Let's try doing question number 8. What we want to do is find all the eigenvalues and corresponding eigenvectors of A. So we know the strategy. We need to look at A minus lambda times the identity matrix, find the determinant, set it equal to 0, and determine the values for lambda that make this hold. So A minus lambda times the identity matrix in this case is going to be the matrix with entries 5 minus lambda, 1, 1, 5 minus lambda. The determinant will be 5 minus lambda times 5 minus lambda minus 1 times 1. And when we set that equal to 0, we find this actually factors to 5 minus lambda minus 1 times 5 minus lambda plus 1. So either 4 minus lambda is equal to 0 or 6 minus lambda is equal to 0. So lambda is 4 or 6. Those are the eigenvalues. Now to find the eigenvectors, we're going to look at the null space of A minus lambda times the identity. So A minus 4 times the identity is the matrix 1, 1, 1, 1. The null space of this would be the vectors that when we multiply the A minus 4 times the identity times the vector, we get 0. Just inspecting it, we find that a vector in the null space of this one would be 1, negative 1, since this matrix times 1, negative 1 does give us the 0 vector. If we look at A minus 6 times the identity, the matrix becomes negative 1, 1, 1, negative 1. And a vector in the null space of this, just again by inspecting, so we don't have to even put it in row echelon form, is 1, 1, since this matrix times the vector 1, 1 does give you the 0 vector. And so the eigenpairs are 4, 1, negative 1, and 6, 1, 1. Now in part B, we want to show that if lambda x are the eigenpair for A, then A minus some scalar mu times the identity matrix times x, that eigenvector, is equal to lambda minus mu times x. And so let's prove that this is the case. So we'll start with one side. We'll say the left-hand side, A minus mu times the identity, that quantity times x. And let's see what we can do here. Well, we know that matrix vector multiplication distributes, so this becomes A times x minus mu times I times x by the distributive property. And this is equal to, well, let's see, we can do a couple things at one time here. A times x is lambda times x, since lambda is the eigenvalue. Corresponding to the eigenvector x for A. And also mu times the identity times x, because of the associativity of matrix multiplication, is just the scalar mu times the identity times x, but that's just the scalar mu times x, the vector x. And so this is by associativity of multiplication product. But we also know that we have scalar multiplication distributes, and so this is equal to lambda minus mu times x by the distributivity of scalar multiplication, and that is exactly what we wanted to show. So it is the case that A minus mu times the identity times x is equal to lambda minus mu times x. Now, what did we really show? We showed that if we know an eigenvalue and eigenvector for A, and we look at A minus some scalar times the identity matrix, then it has an eigenvalue the same as lambda minus the scalar, and the same eigenvectors that A had. Now, is that going to be useful? In part C, it says, give all the eigenvalues and corresponding eigenvectors for B. And it says you can save yourself work if you're clever. Well, that means if I noticed what I was actually proving in part B, and we are clever, so we notice that B is actually equal to A, the problem we did in part A, minus 1 times the identity, which means the eigenvalues of B must be the same eigenvalues as A minus 1. So the eigenvalues of B must be 4 minus 1 and 6 minus 1. And the eigenvectors for B are the same as the eigenvectors for A, which were 1, negative 1, and 1, 1. So we know what the eigenpairs are. It's 3, 1, negative 1, and 5, 1, 1. That's it for 8.